If you use finishing operations, like grinding, see this, no, grinding is what we put it on a grinding wheel. Grinding wheel typically you have grit which are held by some binding medium and it will be rotating. So, grinder can rotate here, or it can rotate here, or you can have something which is they are typically a little like the materials used in your car or for this thing. Next we have, as we come down, lot of finishing techniques, saying as we go down, no, so we have lapping and so on and so on. Measured values, contact resistance of various interfaces have been put here. You have seen this, the last one seemed to be most favorable. Brass to brass with 15 micron tin solder coating. So, the meter square means the total meter square degree Kelvin per watt, total amount of area that is in contact. See, this is very small, it is very encouraging thing. And the other extreme, we have this thing saying, no, iron to aluminum in air, you just put them both together. Similarly, if you are to bond it even with very thin layer of epoxy, we still have appreciable material here. So, let me go back to the very first lecture, first point. Heat flow across the thermal interfaces is complex. Conduction in the interface is parallel and 3-dimensional as the heat appears to squeeze through the points of contact. This is what I was telling you. Heat flow occurs by radiation and by conduction through the interface material. Main thing is conduction here, and because this is closed and you have no other thing, little bit of radiation takes place here depending on the differences in temperature. We can show that convection in the void flow is insignificant if the Rayleigh number is less than 1700, means that there is no flow, which is always the case. It would appear thermal path through the hard points of contact is much more significant than thermal conductance through the void material. Which I said, no, if you ignore this convection in the void material, means no air can circulate, they are almost like closed cells. Research has shown air to have a large impact on the overall thermal conductance when compared with a vacuum. Some amount of this thing happens, meaning even small amount of caught up air will be better than trying to assemble them in a vacuum. If you assemble things in a vacuum, vacuum may not be such a good idea. It may be okay when we want to preserve food materials, but you want to assemble two things in vacuum, it does not matter, but then it does help in trying to push in any other interface material through it. If you want to put a silicon fluid, or if you want to put some other thing which has a higher conductivity, maybe assembling it in vacuum then releasing the pressure may help. It is done in the case of things like our transformers, which are vacuum impregnated. The impregnation uses a vacuum technique, there is not a vacuum inside the atmosphere. That what you call the varnish, something which goes into the surfaces, in those cases aids directly in the conduction, because it hardens a little and you do not have air pockets. If you do not impregnate it, chances are air pockets will form, they have a tendency to expand and contract, and sometimes undesirable things like fungus growth and all can happen. Will it grow at that high temperature? I won't know, but it does create voids and then it makes temperatures this thing. So, we have here, it has been estimated that the actual solid material point to point contact area may be 5% of the apparent area, 90% of the heat path is through the void material, because finding the exact values of is quite difficult. Empirical equations are quite common. You have seen this, the actual surface of the contact area might contains peaks and valleys superimposed on larger waves, superimposed irregularly as roughness. So, we have this what do you call RMS value, you must have heard about 3 triangle finish, 1 triangle, 2 triangle, 3 triangle, depending on they use a lapping compound and try to what you call run it against a different surface, 2 contacts, then something settle down, something gives and eventually there will be a beautiful contact. Once again you remove that and then now pack it with heat conducting material or a silicone material, and then if you squeeze it, what was 5% can eventually increase to probably 75 to 80%. It can't be made 0, so but it will be significantly higher. Then after that next slide also talks to you, it is not just about the material but about this positive curvature, and is there a way of increasing the pressure at the interface. Heat transfer across an interface of 2 materials is very complex. They appear to be of great importance. You understood, no? It is not fully understood except in idealized cases where they have actually taken various type of things. One of them is pressure of the interface and hardness of the contact, size of the contact asperities. So, as you squeeze them more and more, they get flattened out and they meet each other. This positive curvature is very good because it has a tendency to squeeze in. It will happen like when I put both of my hands together, you can see that it is there. Geometry of the contact surface with regard to roughness and waviness, average gap thickness of the void space, thermal conductivity of the fluid in the void spaces. Seen that, no? It is not air, it could be any conductive fluid, and thermal conductivity of the contact materials. So, if you consider the conductivity of the fluid and the contact materials, they have given here this what do you call radius of curvature is mentioned as rho, half of the vertex angle is the gamma. So, the next slide which I showed you earlier gives you lists so many other things. So, typically there are formulations made reasonably useful relationship for the heat transfer interface coefficient as all these things where K1, K2 are the thermal conductivities of material, contact pressure at the thermal interface, that is newtons per meter square, hardness of the softer material. The softer material deforms and flows around the harder material. So, more contact is there. So, if both are hard, obviously none of them give. So, nothing gets formed. That is where when you have things like copper and aluminum, they are generally relatively soft. So, basic aluminum, if it is not anodized, it is the surface is relatively soft. If you have a hard anodic layer, it becomes very, very hard. You do anodize it sometimes to get heat stroke electrical conductivity. All anodic layers are electrically non-conductive, they are insulated. So, we have a problem once again because of the direct following of one to the other. Looking back at these relationships, you see here we have the sigma 1 and sigma 2 square, the RMS roughness of the material. So, if you put it on a what do you call, there are machines where measure these things directly as a small scriber, it is a little like your old vinyl records. So, if you see here we have grooves, vinyl records usually have grooves, there is the that we call the needle, no? Needle goes in the grooves. So, if you have these grooves, the needle goes in the grooves and then on the walls of the grooves you have the audio content recorded on that. So, the what do you call meter, loosely I will call it the roughness meter, also has the same stylus which writes across the surface, and then it will directly give you a output, and then it will give you the RMS value also, saying how much of deviations are there. More value is obviously this thing. So, we have the asperity angles shows a good relationship to test data within the following range. So, when I know this pressure by hardness of the material is less than 0.1, and when K is between these values 13 and 133, when the what do you call the roughness value is within this, and then tan phi is very shallow. Similarly, while this has been made by one researcher, they developed a calculation under the assumption that both the point of contact conductance and void material layer are based on the two heat flow paths being independent. Some effect is a parallel combination. So, they have given all these things, saying thermal conductivity with the gap fluid, and then I mean it's if you know the values, no, everything depends on obviously what is x and all that is possible for you to determine, but then provided you know all the values. So, y by gamma as a function and all these things are already available in case somebody is trying to make a huge what do you call software this thing. But in reality what we do is we follow the nearest available values of this directly degree centigrade per watt for the case, as well as if mounted on a standard heat sink. You have seen here, this I think I showed you earlier. Consult individual data sheets for product specific values. Values given by any book are generally for general reference only, not specific. High effective thermal conductivity board was used for the calculations. You understood, no? It moves a lot. ZX 4 layer, he says. And then I will avoid this. Then we have copper lead frames. Plastic packages are for copper material and non-fused type unless otherwise shown in style. Die size material leads internally to die attach pad significantly influence thermal performance. This is where now it comes to individual data sheets, because individual data sheets after the manufacture they would have taken a relatively large number of samples and give you a minimum effective thing. So, if you see any data sheet, you usually have three values. One is typical and one is guaranteed minimum and guaranteed maximum. So, we are all familiar with sometimes what we think is the thing may not be. Typical value, best example I can give you is your rechargeable cells. Nicely the number 2500 milliampere hours is written, but that is typical. Guaranteed minimum, most of them are 1800. The best lithium ion cell is probably 1800, but they keep depending on the condition of measurement and rate of this thing. It is not a directly multiplication of amperes into hours, milliampere hours. It is also a lot on the rate. So, depending on that condition, the 2500 effectively can become only 1800 guaranteed minimum. Sometimes you will be surprised because of effective management, you may get little more. Heat sink applies to package bottom, and then they have given some other things. Huge amount of thing now these days, packages keep improving more and more and more. Now, I will try to jump to tremendous detail is given here, saying where is the how junction to ambient junction to moving air, the calculations have been made. This is directly available to you on the, it has been retrieved I will say in October 2017. So, variants of it will be available, nothing for you, I mean do not feel lost. If you cannot get this thing at all, the equation usually assumes to be valid for calculating junction temperature theta junction to ambient is a misapplication, because it is a variable function of not just the package but many other system level characteristics. You have seen here, no? I think it is reasonable. Let me just go back a little. The design and layout of the printed circuit board on which the part is mounted. Test board is a heat sink that is soldered to the leads of the device. Changing the design, test board changes the efficiency of the heat sink and therefore the measured RGIA. In fact, the still air JEDEC defined measurements is dissipated from the test board. You have seen that, no? The issue seems to be that things are dissipated from the test board. You understand, no? Even the things which are given by the JEDEC defined theta junction to ambient are not directly the device hanging in air. You too would have noticed it if you are to what do you call test any transistor or any other thing, no, even a small thing like a diode, the rate of heating becomes tremendous and chances are it will fail, because the rate of heating is more and the accumulated heat is there. And then here where no is what I would like to point out. System board rarely approximate the test coupon used to determine so on. So, test coupon is somewhere in the small print it is given here, while the word infinite is not used, impractically large areas are used. This is where it is said when you go to Golden Dragon, that LED mounting and all that GD, I think it is by Ashram. The test coupon itself talks about the pattern to be almost 25 mm by 25 mm, and there is a slug in the middle, and then the leads also have a large pad, while the actual contact pad may be 1 mm by 2 mm, or I am sorry 1 mm by 0.5 mm. It sees a pad which is already 5 mm by maybe 10 mm, and then after that spreading in a triangular way. Same thing about the heat in the slug also spreads all the direction. So, effectively you have almost 25 into 25, 625 square millimeters of area that is there, as compared to if you take two leads and then connect your, if you try to pass 300 milliamperes at 3.7 volts, it will not stand long. You will have a beautiful LED which stops giving light. So, if you go down for a given package outline, it looks like PCB design is the all encompassing thing. Chip or pad size is somewhat partly true, not 100% true, but then you cannot ignore it also. Understand, no? Chip or pad size is partly true. Internal package geometrical configuration, then the altitude, that is where you have the heat carrying capacity of the air, and then ambient temperature, and then power dissipation. It seems to be ambient temperature and power dissipation seem to have lesser and lesser effect than the system level PCB design. So, this is coming from the actual manufacturer, that is Texas. Texas has been in this business forever, as long as at least what I can remember. See this here, so many junction to ambient, no, so many types of shifts. So it is more for you to read about it, saying we have a die-size impact, and then slowly we come to here. If the die size is small and geometry configuration saying pin to pad distances, every known material has been formulated and given here. So it will be easy for you if you can just try to read up these things. Semiconductor, IC and package thermal metrics. We come to junction to case thermal resistance was originally devised to allow estimation of the thermal performance of a package when a heat sink was attached. By definition itself, thermal resistance from the operating portion of the semiconductor to the outside surface of the package closest to the chip mounting area with the same surface is probably heat sunk as to minimize temperature variations across that surface. So we have this problem of even the definition, that is why the word the top starts with the metric. The procedure is some test tube, package is pressure fitted to a copper cold plate, copper block with circulating constant temperature fluid. The next picture is what I have shown you earlier, which I will show you how those things are. Silicon thermal grease or other thermal interface material provides coupling between the cold plate and the package. Insulation is provided around the test coupon to minimize parasitic heat loss, that is because we are measuring it. So we have all this here, we have a thermal grease, then we have a test coupon, we have a cold plate. Finally, based on this, traditional but invalid usage of the junction to case is to calculate the junction temperature of chips operating in a system. Devices operating the system are measured using thermocouples, IR cameras or something mistakenly used to calculate the junction temperature like this. You have seen this, no? This is directly what you call from the manufacturers. So I am just quoting it because I was also surprised about saying the fallacy here is that only a very small percentage of heat energy in a typical plastic package is convected and radiated off the chip surface. Many models have shown 60% to 90% from is convected and radiated off the PCB to which the package is attached. So in the case of aircraft and such applications, if you have a large PCB, show me this, sir. If you have a large PCB like this, you have a lot of components mounted occasionally on both the directions. Usually they have a thick copper area on both sides, here and probably on both the surfaces. The whole thing is attached to a case in which there are grooves, and after you lower it in the grooves, something holds it hard against it. This looks like is a reliable only way of taking away heat. And there are metal core PCBs. The printed wiring board, instead of using the word PCB, let me now change over to the other thing. Printed wiring board has metal core on which an insulator is, I do not know how it gets attached to it, probably there are various methods on it. On top of it you have the conductive thing. So you have a heat conductive core, and both sides of it you have the electrically insulated area, which is getting smaller and smaller. What used to be around I think 400, 500 microns is barely 100 microns now, and on top of it you now have one more time a conductive copper which is thick. So, you have thick copper and then a very thin what you call insulating layer and then conductive core. With that, a lot of heat transfer takes place directly through the PCB itself. If you can make things like that, it will make life easy for chip mounting technologies here. So, we have usually huge this thing thickness of interface and so on. So, we have huge amount of what you call way of calculating and making things. So, depending on the airflow and so on, the measurements are calculated. So, maybe at this point now I will go back to the good old thing here. Say a printed circuit board, then we have all these thermal resistances, and this is where why I am stressing on this is, though what is directly quoted on the device, like if you take a TO223 package, happily they say internal resistance is so much from the chip to the surface of the case, that itself usually little variation is there, that now has to be mounted on a heat sink or onto the PCB. So, if you go down, we have all these more and more what you call complicated things. I suggest you read them out yourself. Same thing, this is the good old Japan radio company. Read up what has happened of how the word RCA Victor and all has come. Now, this particular thing is called the New Japan Radio Company. They have also given similar things about it. So, you have what is the thermal resistance and measurement and so on, but in the end, after a little while you will notice that you have no choice but to conduct a empirical experiment before you finalize the design. So, we have all these models and how to circuit, how to make it and how to generate heat in the first instance. So, at this point I will so we have so many of these things saying what is the power dissipation on a 2-layer board, 4-layer board, anything you can think of is probably already has been calculated and kept. So, you should be able to search for these things and try to implement them as much as you would like to implement. My call also locate the retrieve this information directly whenever say this being recorded in the end of 2017, I expect nothing has really changed in the last 10 years. Maybe the next few more years these are still valid and then you can start working on it. So, thank you.